Called the high voltage transmission in transformer in power station. After we've designed our transformer and we've built a power station to generate electricity. The electricity that is produced needs to be transmitted to our various residential area, offices, industries, and so on and so forth. It needs to be moved across from one region to another region within a country or within countries. So why do we have to step up? Because when we describe a transformer, we say it's an electromagnetic device that is used for stepping up voltages or stepping down voltage with the operating frequency remaining same, remaining constant. So why do we have to step up voltage? When we manufacture or when we produce, when we generate a voltage about 11,000 volts or about 415 volts, why don't we just transmit what we produce? Why do we have to step it up? Why do we need a transformer to raise the value to a higher value in order to transmit? So here are the reasons why we have to do high voltage transmission, why we need a transformer, a step-up transformer to raise the value of the electricity that is produced before we transmit this electricity to our homes. Now, transformers have number of roles they play. Like we said, they can step up, they can step down, and so on and so forth. They can stabilize, correct, and so on and so forth. They used to increase the potential difference, that's the voltage of electricity, before it's being transmitted across the entire national grid, across a country. Electricity transmission is called a grid. When we build a system wherein from the point of production of electricity or generation of electricity to the distributing end, our homes, that whole holistic network of taking the electricity is called a grid, a national grid. The transmission lines, they are called the grid network. They are called the grid network in a country. So one of the jobs a transformer does is to increase the potential difference of the electricity that you produce or that you've generated before it's being transmitted across to the national grid. And another thing is that they use to lower also the high voltage electricity that is used in the power lines to the lower voltages that are needed in our homes. So after you've transmitted it, this voltage, because the reason why we raise it is so that we don't lose it. Because when you raise it, the current cannot be lost. It's protected. Okay, when you get it to the end usage where you need it, you don't use 400,000 volts in homes. The whole homes will catch fire, will start to burn. So we have to bring the value down. We need another transformer that is designed as a step-down transformer to bring the value down. Okay, we have to bring the value down, to reduce the voltage to the desirable value that we need in our home. So a step down, that's where we need a step down transformer to bring the value down when it's about to get to the homes. So if you go to some third world nations, transformer, you can easily see them in your street. Every street probably should have a transformer to bring down the value of the voltage, 11,000 voltage that is coming to that street to 230 voltage that is desirable for homes. So that's what the transformer does. It step up values of voltages in the power station to very high values so that we can transmit over long distances, and then get it to our homes or our streets. We have to bring the value down to a desirable value that can be that is adjustable, that is usable by the home appliances. So on that note, we have two types of transformer: the step up and the step down transformer. They also use as adapters also to add the main voltages to the electronics equipment like the hair dryer, the driller, and so many other electric motor devices that we use in our homes. So transformers are built in even in our deck, what do you call this system? Music system. The deck system you have in your home, for those who have the big CD compact disc players, you have a transformer inbuilt in it in order to, even your television, you watch it right most of the time. There's a transformer that's inbuilt in every television to adjust the value of the voltage that is entering the electronic appliance so as not to burn the electronic. So the transformers are inbuilt devices. Even in this type of transformer, they are tiny transformers. They're very small. They're not like the usual big transformers that are used in the transmission and distribution of electricity. Now let's take a look at the advantages. What are the specific advantages of high voltage transmission? Why do we raise the value of voltages? When we produce, why do we have to raise the value of voltages to a very high value? Why do we have to raise the value of voltages? from the value that is produced to a very high value for transmission. Why do we step it up all the way from 11,000 voltage to 400,000 voltage? Now this is the why. This is the why. Number one reason is that when electricity is transmitted over long distances, the current in the wire hits them, resulting in energy loss. So when you are transmitting the long distances, the small current that is flowing in the wire will get heated up. It will become I square arrow. That current will become this I square arrow that I made mention of earlier on. It will become the I square arrow, and it will be lost. It will become this one. It will become a heat loss I square arrow. The current gets heated up with the wire, and then you lose it. So if you are sending the voltage in with small amount, before you reach the destination, you would have lost almost everything. You would have lost almost everything. So this is one of the reasons why we step it up, so that we don't lose the energy before it gets to the destination. Okay. So to transmit the same amount of power as the input power, the potential difference at which the electricity is transmitted should be increased. So if you want to transmit the same amount of power as the power you put into the transformer, the input power, you want to transmit that equal amount of power, you have to increase the potential difference. You have to increase the potential, the VP. Remember, V is equal to IR. Remember, V equals to IR. Okay? V is equal to IR. Voltage, according to Ohm's law, voltage is equal to IR. So if you don't raise the voltage, the current will be affected. The current will heat up and become heat. Will be lost as heat. It will change to I square arrow. Become I square arrow, and it will be a loss. To no longer be a voltage, it will be a heat. This is heat loss. It's a form of power, but it's energy that is being lost. It's power that is being lost. Okay. So when that happens, you don't get what you transmitted. You don't get what you transmitted. So to solve this problem, this will result in small current being transmitted through the power lines, because P equals to IV. So if the voltage increases, I must decrease to transmit the same power. Okay, to transmit the same power. So a smaller current flowing through the power lines result in less heat. Smaller current will result. So if you raise the voltage, the current that is flowing will now small, will result to less heat being produced in the wire. So if you raise the voltage to a higher value, the current becomes small. Okay? If you raise the voltage, the current becomes small. Are you with me? If you raise the voltage, the current will become small. Because if you take a look at this, P equals to IV. P equals to IV. So we say I equals to P over V. P over V. So it will be inversely related. If I raise my V, if I say V will be P over I. P over I. P over I. Or similarly, if you want to use this, if you make R the subject, R will be V over I. So if you look at it, if you increase the voltage, the current will become small. Use this one. Let's use this one. In transmission line, if you increase the voltage, the current becomes small. So if the current is small, there will be small heat loss. That's why we always raise the voltage. We raise the voltage so that the current becomes smaller. Okay, there will be less heat loss. If you transmit what you produce, there will be so much heat loss, and then you don't get desirable amount of current in the station, in the receiving end. You don't get the desirable amount of current that you needed in the receiving end. Okay, so here is a power station where electricity is produced, and then we put up a step-up transformer to raise the voltage, and then it becomes a high voltage, low current. That's what it is. High voltage, low current. From this equation, high voltage, the current is low. You can see they are inversely related now. Inversely related. High voltage means, in this case, means low current because of inverse relationship. Because of inverse relationship. High voltage, low current. So when you do that, when you raise the voltage, current will be low. Once current is low, there is no much loss. So I'm getting to almost where you're going to give it to the homes, you step it down. This high voltage, you have to bring it down to a desirable value before you distribute to the home. So this is how energy is being transmitted in our home. Now let's take a look at quickly for the extended IGCSE people. Now we say the power, which is the heat loss, power in form of energy per second. Power means energy per second. Because power is, energy is electrical energy. I'm not talking about the mechanical energy. Electrical energy is IVT. Current times voltage times time. Current times voltage times time. Okay? This is the energy. So the power is energy over time. Okay? If I want power, I will do like this. I will say energy over time. Right? So here also you divide by time. If I want power, you divide by time. You divide by time. So if you want power, this time will cancel this time. So power will become IV. Power will be what? IV. Power is what? IV. So that's why power is IV. That's why power is IV. That's why our power is electrical power is IV. But this power is energy per time. Energy per time. Energy per seconds. Okay? Power is energy per second. Energy divided by time means energy per second. So when you're talking about power, you're saying energy per second. Okay, that's the meaning of power. Energy per second. And energy is in joule, which means joule per second. You can simply say joule per second. You can simply say joule per second. You can simply say joule per second. Okay, when you're referring to power. Okay, so we say the power or energy per second or joule per second lost in the wire when you're transmitting is given by this. I've already explained this. I square R. The power loss or the heat loss is the I square R. So if they ask you to calculate the heat loss in transmission cable, you say P, the heat loss in transmission cable, you simply say P for heat loss. You know, this heat loss is in form of power, okay? You say is equal to I square, the square of the current multiplied by the resistance in the wire. The square of the current multiplied by the resistance in the wire is the heat loss or the power loss. We either call it power loss or we call it heat loss. We either call it power loss or we call it heat loss. But the energy itself is simply, remember we said here, we said energy is power times time. Now if you cross multiply, see, power is energy over time. Energy is power times time. So energy is what? Power times time. Power times time. You know power is IV. That's why we got IV energy to be IVT. Power itself is IV. If we change the color, power itself is IV. This power itself is IV. And then when you bring down this T, become IVT. So energy, they can ask you to calculate electrical energy. They will give you the current, the voltage, and the time it takes for whatever has happened. So you should be able to use this to calculate your energy, electrical energy. Okay, it's different from the energy that you work done over time, taking that's power, or energy that you're doing before. In this case, the energy is electrical energy. The current in the air dryer multiplied by the voltage supplied to the air dryer and multiplied by the time it took you to dry your hair, you get the energy that is being used, that is consumed by the hair dryer. Okay, then they ask you to calculate the power, useful power. If they want the useful power, you use this one. This is useful power. Useful power from the hair dryer. Useful power loss, you use this one. Okay, this one is for useful power. For us to calculate the useful power from the hair dryer. Useful power from the hair dryer. Okay, if they ask you to calculate the power loss, this one. Either they say power loss or they say heat loss. Okay, we use this one, I square R. The power loss or heat loss, we use the I square R. Power loss or the heat loss. Is that okay? So these are the questions that can come from here in Cambridge. Okay, we already know the transformer equation. These are the questions that Cambridge. We know the ID equation, IPVP equals to ISVS, ID equation. These are the questions that can come from here in IGCSE, Cambridge IGCSE. Okay, so with this, we've come to the end of this. Next class, we will see what topic we have.